Hey everyone, welcome to the third video of Vic Explains Calc 3 Concepts. So for today's lesson, we're going to be going over line integrals, parameterizations, and the fundamental theorem of calculus for line integrals. So let's get started here with problem 1. So it says, consider the vector field f equals xi plus yj, and let C1 be the line segment joining the points 1, 0, and 0, 2. And let C2 be a curve joining the same points, which can be represented in two ways, as a parabolic curve of degree 2 and as a part of an ellipse. And then this graph shows the situation right here. So if we go over here to the instructions, the first step is going to be to compute the line integral over C1. So let me go to my work here real quick. All right. So I just once again just redrew the graph right here, and I just wrote f equals xi plus yj. And then I got the steps right here to compute the line integral. So the reason I know these steps is if we go back to the notes here real quick. Yeah. Okay. So whenever we want to compute the line integral over a curve C, the first step is always going to be to parameterize C, right? And this essentially just means we just want it to be the position vector, right? We want to get the curve C and make it as a function of t, right? That's pretty much what this means. So if I go to my work here real quick, we have the position vector RT, and that equals 1 minus 1 half TI plus TJ. And then the way I got this right here, if I also go back to the notes again, we have this right here, the parametric equations of a line that passes through this point right here, and that's parallel to a vector like this here. And it's going to be x equals x naught plus at and y equals y naught plus bt. And then we can ignore z because we're not working with that right now. So then if we take this right here and go back to our problem, right? So let me see. So for x naught, y naught, that's essentially just going to be our starting point, right? So our starting point of this line segment right here is going to be the point 1, 0, right? So for the x component right here, the y component, I put the x component here and the y component here, right? So the x naught, 1, I put right here. And then the y naught is 0, so I just didn't have to put it right there. And then as for the vector that it's parallel to, right, with AI and bj, if I go back here, I use the vector negative 1 half I, which comes to the left here in the x direction, 1 half. And I used plus 1j, which comes up in the y direction here, right? And then that forms this vector right here. That's going to be parallel, right? So I got, so then, so I said negative 1 half I and plus 1j. So that means A is negative 1 half, and that means B is 1, right? So if we go back here, we'll have 1 minus 1 half t for the x component, and then 0 plus 1t for the y component, right? So that's how I got this right here. But one important thing to consider is which values of t are we going to be using, right? So I chose that t is going to be from 0 to 2 seconds, right? And the reason I chose this is because when it's at 0 seconds, I want it to be right here, right? Because this is the starting point. So if we plug in 0, we'll see it's going to be 1 minus 1 half times 0. So that's going to be 1 plus 0, right? That just leaves us with like 1 for the x direction, right? So 1, 0, that's our starting point right there. And then we know if we put in 1 for t, it'll get us this point right here at 1 second. And then if we plug in t equals 2 seconds, we'll get the 1 minus 1 half times 2. So 1 minus 1, it's going to be 0 for the x. And then we'll get 2j, so that's going to be 2 for the y. So we'll get this point right here, right? So that's why I use t between 0 and 2. So then step 2, if we go back to our notes, is going to be substitute the parameterization RT into f. Okay, so once I did that right here, so it's just going to be the same function pretty much because it's xi, right? So I put the x component into x right here, and then I put the y component of RT into y right here in f. So it's just going to be the same function, right? And then the third step is going to be to compute r prime of t, right? So if we go back here, that's just take the derivative here with respect to t. That's going to be negative 1/2 I, right? And then take the derivative here again with respect to t. That's going to be 1j, right? So that's it right there. And then step 4 is going to be to take the dot product of f evaluated on c, blah, blah, blah. It's just f dot r prime, right? That's going to be step 4. So f dot r prime. So let me see. So when we multiply the two x components, we're going to get negative 1/2 plus 1/4 t, right? And then when we multiply these two y components, we get just plus t. So then when we add this up, we're left with 5/4 t minus 1/2. And then for step 5 is finally when we integrate along the curve from a to b, right? So we have right here, just grab this right here, f dot dr, right? Grab this, put it in here. And then the reason we're using from 0 to 2 is once again what I was explaining before, how we want to use t from 0 to 2, right? So integrate this from 0 to 2, we're going to get, what is this? Yeah, so 5/8 t squared minus 1/2 t, right? And then evaluate this from 0 to 2, right? So if we put in a 2 here, we get 4, 5/8 times 4. It's going to be, what is that? 4, 2, so like 5/2. And then minus 1/2 times 2. What is that like? Minus 2/2. So is that 5/2 minus 2/2? Yeah, it's 3/2. All right. So that's gonna be our answer for step 1. Right? Okay. We got line integral f dot dr, right? That's what we got here. 3/2. Okay. So now let's go on to step 2, which is gonna be to compute the line integral over C2 using two different parameterizations, right? And then the first method is going to be to use a parabolic curve. All right, so let me go back here to my work. All right. So the way I did this, right? We know that the position vector RT is going to have an x component and a y component, right? The issue is, how do we find these x and y components? So I started by just using the vertex form of a parabola, right? Because we're doing C2 right now, right? So C2 is this right here, right? So we want to use like a parabola that's pointing downwards, and we want to evaluate it from here to here, right? So let's just start by finding the equation of the parabola, right? So we have the vertex form right here, and we know that the vertex is at 0, 2, right? So we know our h is 0, and we know our k is 2, right? And then for x and y, let's just substitute in 1, 0, right? That's just our point that we know right here, right? So with this vertex form equation, we want to substitute in these 4 values in order to find this a that we don't know here, right? So then once we substitute in all these values, we're left with a equals -2. So now when we get this right here, y equals ax minus h squared plus k, and then we put in -2 here, then we put in 0 for h and 2 for k. Now we get the equation of our parabola right here, right? It's going to be y equals -2x squared plus 2. But the issue we have here is we want this as a function of t, right? As a function of time. So how we're going to get around this is we're just going to replace the x with t, right? And then, and we just say that x equals t, right? So when we do this, we get the same parabola, right? It's just now we have it as a function of t. It's just the only issue with this is that the same way as in with the y and x, right? It's gonna be moving this way, right? How as the x increases, the y is decreasing. And then that's an issue because we want it going in this direction. So I'll get back to that later, but just keep that in mind. So now that we have our x component and our y component, we're gonna put that into our position vector right here, right? So we get RT equals TI plus -2t squared plus 2j, right? And then step 2, right, as we know from before, is just gonna be to find f of RT, right? So f of RT, we know once again, same as the first problem, it's just going to be the same as RT because in this situation, f is just xi plus yj, right? So we can just copy paste right here. And now the third step, once again, compute r prime of t. So that's just going to be right here, just 1i. Then here it's -4t, and then this just becomes 0. So -4tj. All right. And then step 4, once again, just f dot r prime, right? So that's going to be, let's get the x components, t times 1, which is t. Then here we get 8t cubed, and this times this is -8t. And then when we add that all up, we're left with 8t cubed minus 7t. Finally, step 5, just integrate from a to b. All right. So, yeah, okay. So, as I was saying before, normally when we have a parabola like this, right, we have this equation right here. It moves from left to right. So instead, what we're going to want to do here is we want to specify that we want to integrate from 1 to 0 instead of from 0 to 1, right? So just remember, so specify here, integrate from 1 to 0 in order to move in that direction right there, right? However, we can't really integrate like this. So we have to use this rule right here that I actually forgotten about, but it's the reverse integral rule, right? Where if you have the integral of fx dx from a to b, that's also equal to the negative integral of fx dx from b to a, right? So we just flip the bounds and make it negative, right? So if we go back here, that's what we did. So I just made this negative, and then I made it from 0 to 1, right? So when we take the integral of this, we're left with, what is that? Okay. We're left with this right here, right? 2t to the 4th minus 7/2 t squared. And then when we, oh, let me see this right here. 2 to the 4th. Yeah. Okay. Sorry about that, guys. So yeah, so when we integrate this here, we're left with 2t to the fourth minus 7 halves t squared. And then when we evaluate this from 1 to 0, we're left with 3 halves. Once again, just like as in step 1, right? All right, so now go back here to the problem. Now that we use the first method of using a parabolic curve, now we have to use a second method where we want to interpret C2 as part of an ellipse. And this method I like a lot more. This one's a lot easier. So yeah, so step 1, same as before, just find R of t, find the position vector, right? We want to parameterize C. So how do we do that as an ellipse? So we have to use, oops, sorry about that. I'm here. So we have to use polar coordinates, right? So the polar coordinates for the x component is going to be r cosine t, where r is the radius of the circle or ellipse. And yeah, the y component is going to be r sine t, where once again, r is the radius of the circle or ellipse. And then keep in mind, this is assuming that you're going in the counterclockwise direction, right? Okay, so let me go back here to my work. So for the x component, it's r cosine t, but in this case, the radius is just 1, so I just put cosine ti. And then the y component, once again, r sine t, and then for this part, the radius is 2. So 2 sine tj. And then I chose that I wanted t from 0 to pi over 2. And the reason I chose this is because now that we're using polar coordinates, right? We're using radians now. And then if we want to travel from here to here, this is a quarter of a circle, right? This is a 90-degree angle, which is the same as pi over 2 radians that we traveled right here, right? So that's why I used from 0 radians to pi over 2 radians, right? That's why I used those values for the t. And then once again, step 2, as we know from the previous uh 2 parts that I solved, it's just the same as RT, right? F of RT equals RT. And then step 3 is find R prime of t. So if we go back here, it's just negative sine ti plus 2 cosine tj, right? Pretty easy stuff. Step 4, f dot r prime, right? So we want to find this times this. What is that? Negative cosine t sine t, right? And then this times this. So 4 cosine t sine t. And then when we add these two up, we're left with 3 cosine t sine t. Okay, so now for step 5, we want to integrate from 0 to pi over 2 radians, right? And then integrate 3 cosine t sine t dt. So for this, you want to use u substitution. So I just decided to choose sine t for u. And then so du is cosine t dt, right? So right here, so it's going to be 3u, right? And then cosine t dt we know is du, right? So 3u du is going to be the new integral with u sub. So then we do that. We're left with 3 halves u squared evaluated from 0 to pi over 2. But when we have this 0 to pi over 2 right here, this is using t, but we're using u here. So we have to substitute sine t back into u in order to evaluate it at these 2 points right here. So once we do that, we have 3 halves sine squared t evaluated from 0 to pi over 2. And then we know that sine squared of pi over 2 is 1. And we also know that sine squared of 0 is 0. So it's just 3 halves 1 minus 3 halves 0. And then finally, we're left with, once again, 3 halves. All right, so now let's go to the third step of the problem. We have to use the fundamental theorem for line integrals, right? So first thing we want to do is determine if f is conservative, right? So let me go to my work right here. All right, so I just said f is conservative, but why is it conservative, you might ask? So let me go here real quick. And okay, yeah. So if for any 2 points, P and Q, the line integral of f dot dr along the curve C has the same value along any piecewise smooth path C from P to Q lying in the domain of F, then the vector field F is said to be path independent or conservative. All right. So let me just go back here. Right. So pretty much what this is saying is that if you have 2 points, right, let's call this P, let's call this Q, and you take two different paths and they result in the same value of the line integral, right? Yeah, right. So we got one path right here, C1, and the line integral we got was 3/2. Another path here, C2, line integral we got was once again 3/2. Then we know that the vector field F is conservative, right? So that's why I said here F is conservative. So now we want to find the potential function f of xy such that such that f is just gradient of f, right? Or let me say this, such that vector field f is equal to gradient f, right? That sounds a bit better. So how do we find this potential function? So let me go back up here. So we're assuming that this is just the gradient of f. So we want to find the original function f, right? So we got to kind of take the integral here in order to find that, right? So we know that if this is a gradient vector, we know that this is f sub xi plus f sub yj, right? So we know that f sub x is equal to x and f sub y is equal to y, which is what I wrote here, right? So we know that if f sub x is x, then f must have been 1/2 x squared plus some function of y right here, right? And then same here. We know that if f sub y is y, then the original function f must have been some function of x plus 1/2 y squared, right? So if we just combine these two right here, we're left with the potential function of 1/2 x squared plus 1/2 y squared plus some constant a. So there, that's our potential function right there. And then if we go back, the next step they want us to do is now to use the fundamental theorem for line integrals to compute f dot dr along the curve C for the path from 1, 0 to 0, 2 using the potential function f. So let me go here. Yeah, okay. So how do we use this fundamental theorem for line integrals that they're talking about? So let's go to the notes here once again. So right here, it says that, yeah, so we know that vector field f equals gradient of f, which we just found the potential function for it. So we know that the fundamental theorem of calculus for line integrals, it tells us that this right here, integral f dot dr, is going to be equal to the integral of grad f dot dr, which is equal to fq minus fp, right? So I just copy paste, wrote that right here, right? So that's what we're looking for. We're looking for integral of f dot dr along the curve C And this equals FQ minus FP according to the fundamental theorem for line integrals, right? So, so what's Q and what's P? So we're just using P as a starting point, right? So it's going to be 1, 0, and Q as the ending point. So 0, comma 2, right? So f of 0, comma 2 for Q and minus f of 1, 0 for P. So let's see. So if we just plug in 0 and 2 into this potential function f, and we can just ignore a for these purposes. So we get 2. And then if we plug in 1, comma 0 into here, we get 1/2. So 2 minus 1/2 is once again 3/2. All right. So let me go here. All right, so that's step 3. So now step 4, we want to verify our results. We want to see if the results from all different approaches gave us the same final answer. So let's check. So we have the first approach, right? Where you want to treat it as a line segment. We got that the line integral was 3/2. Put that in blue right here. And then the second approach, we want to compute the line integral over C2 and treat it as a parabolic curve. And we got 3/2. I put in purple here. And then the third approach, we want to once again compute the line integral over C2, but this time as an ellipse. And we got 3/2. And finally, using the fundamental theorem of calculus for line integrals, we again got 3/2 for the line integral. So everything checks out. All 4 answers are in fact the same. Y confirms the field's conservativeness and the path. Okay. So we know that all the answers match, and this confirms the vector field's conservativeness and the path independence of line integrals, right? Why does it? So conservativeness and path independence, that just means pretty much the same thing, right? It just means that if we go here, if we have these 2 points, let's call this P, let's call this Q, right? It's saying that if it's path independent or conservative, that no matter what path we take here, right? We could get this, go here, make a big squiggly line, come here, or here we take a straight line, or here we do the curved line like we did here in C2 and C1, right? No matter what path we take, we're still going to be left with the same final answer. And our 4 results do show this, which is why we know that it's conservative and path independent. All right, so now we got problem number 2. So we want to consider the same vector field, f equals xi plus yj. And we want to let C be the triangular path that starts at 0, 0, which is this point right here, goes to 1, 0, and then to 0, 2, and finally returns to 0, 0 along this triangular path right here, right? So our first step for this problem is going to be to compute the line integral over each segment of C, right? So in order to do this, we start with part A, which is to parameterize each segment of the triangular path C. So let's start with segment 1, right? From 0, 0 to 1, 0. And let me go to my work here real quick. Zoom out real quick. Okay. So there you go. All right. So once again, I just wrote that f equals xi plus yj, and I just drew the little triangular path here of the curve C. So part A, we want to find, we want to, let me go back here, parameterize each segment, right? So segment one, right, it's going to be R of t of segment one. I said that it's ti from 0 to 1, right? So let's start here. So this is segment one right here, right? So we're using the same formula right here, right? X equals x naught plus at, y equals y naught plus pt, right? Yeah. Okay. And then we know that that here it's only gonna be moving in the x direction, right? So there's no j value. It's just gonna be the I, right? So it moves in the x direction. So after 1 second, it moves once, which is why we just use t and we just did from 0 to 1, right? At 0 seconds, it's at 0, and at 1 second, it's at 1. So we just use ti. And then for the second line segment, it's going to be from 1, 0 to 0, comma 2. But wait, we just did this in the previous problem, right? Let's see right here. Yeah, it's C1, right? So we already found this. So we know that it's 1 minus 1 half ti plus tj for 0 to 2. Let me go back here. So, yeah, so we don't even have to do the work here because we already did the work before. So boom, this right here. And now for the third line segment, from 0, 2 to 0, 0. So for this, I did 2 minus tj. This is because, once again, if you look here, we have no x component, right? Because it's only moving vertically. And then the y component is y naught plus bt, right? Well, y naught is 2, right? 2. And then for b, I chose negative t, right? Because it's moving down, right? So negative t. And then I chose t to be between from 0 and 2, right? This is because at 0 seconds, it's going to be up here, right? 2 minus 0 is 2. It's up here. At 1 second, it's going to be in the middle right here. 2 minus 1 is 1. And then at 2 seconds, it's going to be 2 minus 2. It's going to be down here at 0, right? So which is why I chose from 0 to 2. So now we have part B. Part B asks, for each segment, calculate the line integral f dot dr along the curve CI directly using your parameterizations, right? So if we go back here, we're left with this right here. Yeah. So I just wrote this here to save a little bit of time. We know that for all three of these line integrals, we know that f of rt is just going to equal rt, right? Because f is equal to xi plus yj, right? So if we just, yeah, we already went over this in the last problem. So, so yeah, so our prime of t for line segment 1 is 1i, right? So if we do f dot, f dot r prime for line segment 1, we get, what do we get? So we get t times 1 is just t, right? Integrated along, integrated from 0 to 1, right? So from 0 to 1, integral of t dt, right? Which is t squared over 2, plug in 1, it's just 1/2. Boom. So now we want now we want to find f dot dr on the curve C2, right? And once again, we already solved this in the last problem. We know it's 3/2. So now the third line segment. We already know f of rt is gonna be r of 3t right here, 2 minus tj from 0 to 2. So now we want to find r prime of line segment 3, which is gonna be, this becomes 0, it's gonna be -1j, right? So once again, f dot r prime is gonna be, let's see right here, -1 times 2, get -2. -1 times -t, we get plus t. From 0 to 2, dt. So when we integrate this, we get -2t plus t squared over 2. And then we want to evaluate this from 0 to 2. And then once we do that, just easy algebra, we get -2. All right. So these are our three line integrals, right? From here to here is 1/2. From here to here is 3/2. And then from here to here, it is -2. All right. So now, we want to sum the three line integrals to find the total line integral along the curve C, right? Along this triangular path here. And we want to show that the result is 0. So let's see. So the total line integral along this curve C is going to be the line integral of line segment 1 plus the line integral of segment 2 plus the line integral of segment 3. All right. When we add those three up, we get 1/2 plus 3/2 plus -2. And then we do in fact get 0 as the problem suggests. So now we want to once again verify this using the fundamental theorem for line integrals, right? So part A, determine if F is a conservative vector field. So we know this. We know this from problem 1, right? Because we have the same vector field, F equals xi plus yj. We know that F is conservative, right? So now part B. If F is conservative, find a potential function f of xy such that the vector field F equals gradient F. Again, we already found this potential function. It's 1/2 x squared plus 1/2 y squared plus a. So finally, part C, we want to use the fundamental theorem for line integrals to compute the integral of f dot dr along the curve C over the closed path C and confirm that the result is 0. So let's see right here. All right, so the fundamental theorem for line integrals suggests that f dot dr integral along C is going to equal fq minus fp. But the thing is here, q represents the ending point and p represents the starting point. But since this is a closed path, right, we have the same starting and ending point, right? It's just f of 0, 0 minus f of 0, 0. So we know that anything subtracted by itself is just 0. So we have proved, using this fundamental theorem, that f dot dr is 0, just like our work in part 2 shows as well. And this makes sense. Let me see. Yeah. And this makes sense. We can go to our 18.4 notes, and we know that if a vector field F is path independent, which we know it is, right? We said it was conservative, which is the same thing. Then f dot dr, integral along the path C, is going to equal 0 for every closed curve C, which is exactly what we found here, right? We have this closed curve 0. So the line integral is in fact 0. All right, so that concludes today's lesson, guys. I hope you enjoyed, and I hope you were able to learn something. And that's all for today.